Hello everyone, in this video I will introduce our final regression model for M3 practice Hackthon. I will explain how the model was built, how we improved its performance, and how we assessed and ensured that the model was well fitted. The goal of this assignment was to minimize prediction error, specifically mean squared error, while also making sure the model generalized well rather than overfitting the training data. The dataset includes demographic, behavioral variables such as age, sex, BMI, number of children, smoking status, and region, with medical insurance charged as target variable. From early exploration, it was clear that this dataset has strong nonlinear patterns and interaction effects. For example, insurance charges increase much more sharply for smokers than non-smokers, and this affects these effects become stronger as age or BMI increases. There are also outliers where a small number of individuals have extremely high medical costs. Because of these characteristics, simple linear regression models were not sufficient. This motivated our decision to use a tree-based ensemble method, specifically XGBoost, which and naturally capture nonlinearity interactions and threshold effects. Our model is an XGBoost regressor. Conceptually, XGBoost builds many small decision trees sequentially, where each new tree focuses on correcting the errors made by previous trees. In this dataset, early trees tend to learn high-impact rules, such as smokers generally have higher insurance costs. Later trees then focus on more specific residual patterns, such as older smokers or smokes in high BMI. This iterative correlation process allows the model to fit complex patterns without relying on single overly complex trees. This graph is some part of the result from XGBoost models, which shows some relationship between uh, the variables like BMI and insurance price, age and insurance price. Yeah, here we can see that the insurance price distribution. So to improve the model performance, we focused on the controlled increases in the model complexity rather than aggressive tuning. First, we use cross-validation to evaluate performance instead of relying on a single train test split. The model was trained and evaluated across the specific folds, and we reported the average RSE. This ensured that the performance improvements reflected consistent generalization across different subsets of the data. Second, we carefully select the hyperparameters to manage the bias variance trade-off. The model uses a low learning rate combined with a relatively large number of trees. This allows the model to learn gradually and prevents it from overreacting to noise or outliers. We also limited the maximum tree depth to a very shallow level. This prevents the model from memorizing individual observations and forces it to learn broader, more general patterns. Additionally, row subsampling and feature subsampling were used so that each tree only sees part of the data, which further reduces the overfitting and improves the robustness. Regularization parameters were included to penalize unnecessary splits and excessive complexity. Together, these choices help ensure that the performance improvements are meaningful and not driven by overfitting. Beyond the performance, we explicitly assess the model fit using learning curves, which is a key requirement of this assignment. The learning curves plot training error and cross-validation error as the training sample size increases. In our result, training error is low but not unrealistically close to zero, and validation error decreases steadily as more data is added. Importantly, the gap between training and validation error narrows. This pattern indicates that the model is neither underfitting nor severely overfitting. Instead, it shows a balanced bias-variance trade-off, suggesting that the model is well-fitted and generalizes well to unseen data. Because curves coverage, additionally regularization was not strictly necessary. We also examined the feature importance with XGBoost provides naturally through its tree structure. Feature importance shows which variables contribute most to reducing prediction error across all trees. The most important features were smoking status, age, and BMI, which allies well with domain knowledge about medical insurance pricing. This confirms that the model is learning meaningful patterns rather than noise or spurious correlations. After training the final model on the full training dataset, we generalized the prediction for the test set and created the Kaggle submission file. When examining individual predictions, the outputs were internally consistent and reasonable. For example, young non-smoker with low BMI had relatively low predicted cost, while smoker with high BMI or older age had substantially higher predicted cost. This consistency across examples further supports that the model behaves in a realistic and interpretable ways. In summary, we improve the model performance through careful hyperparameter tuning and cross-validation, and we assess the model fit using learning curves and feature important analysis. Rather than optimizing purely for leaderboard performance, we prioritize the model reliability, interpretability, and diagnostic evidence. This project reinforces the importance of combining performance metrics with fit assessment to build trustworthy medicine learning models. That's all. Thank you very much.